Hello. Today I will show you how to carry out stoichiometry calculations quickly and accurately using an easy-to-understand method. A typical stoichiometry problem includes a balance equation and is usually solved using dimensional analysis in a manner similar to multi-step unit conversions. Because multiple steps are required to reach the answer, students often spend excessive amounts of time learning the mechanics of dimensional analysis and focus on the method rather than the underlying principle. This is frustrating for both student and instructor alike. Here at Texas State Technical College, we have developed an alternative method that reduces both the time the students spend solving stoichiometry problems and the number of errors that they make. As a bonus, the time required to master the equation-based method is shorter than the time required to master multi-step dimensional analysis. I will present today 3 typical examples that I'm going to solve using the equation-based method. Example 1 is a typical stoichiometry problem complete with balanced equation. Today, though, this balanced equation will play a starring role rather than the supporting role it plays in dimensional analysis. The first step in the equation-based method is to identify the substances that are pertinent to solving the problem. In this case, carbon dioxide and sodium bicarbonate. Next, because both carbon dioxide and sodium bicarbonate are described in terms of grams, we will calculate the number of grams present in the balanced equation. Notice that 168.01 grams is the sum of the molar masses of each element multiplied by the number of moles present in the balanced equation. 2 sodiums, 2 hydrogens, 2 carbons, and 6 oxygens. 1 carbon and 2 oxygens. The third and final step is a simple one-step conversion. Our starting point is the given amount of sodium bicarbonate in the written problem. Our conversion factor comes from the balanced equation, the values in the balanced equation. Notice that the 2 values having the same unit, grams of sodium bicarbonate, are placed diagonally to each other so that the units cancel out. This gives our answer the desired units, grams of carbon dioxide. My next example is a limiting reactant problem. It has 2 given amounts of reactants and a single product of interest. It's easier to solve a limiting reactant problem by viewing it as 2 separate problems. The first problem asks how many grams of lithium nitride are produced when 12.3 grams of lithium are reacted. The second problem asks how many grams of lithium nitride can you get from 33.6 grams of nitrogen gas. After identifying the pertinent substances, we calculate the mass of each substance present in the balanced equation. 41.65 grams of lithium, 28.014 grams of nitrogen, and 69.66 grams of lithium nitride. We then solve both problems. The given amount from each problem It's written here. And the conversion factor comes from the balanced equation. Notice that the two values with matching units are still placed diagonally to each other to cancel the units. Then again, the process is repeated for the nitrogen. The given amount from the problem and the conversion factor from the values in the balanced equation. Notice again that the matching units are placed diagonal to each other so that they cancel. According to our calculations, we have enough lithium to produce 20.57 grams of lithium nitride and enough nitrogen to produce 83.55 grams of lithium nitride. Obviously, we will only produce the smaller amount because when the reaction reaches the production of 20.57 grams of lithium nitride, it will run out of lithium. Our third example is also a limiting reactant problem and will also be treated as two separate problems. As we identify the pertinent substances, please notice that the manganese 4 oxide is given in terms of moles rather than grams. When we go to the balanced equation, the manganese oxide is written in terms of moles. Both hydrochloric acid and chlorine gas are written in terms of grams. All of them, however, match the units given in the problem. We then solve both problems. The given amount from the word problem and the conversion factor, once again, from the balanced equation. Notice again that the matching units are placed diagonal to each other, so they will cancel. The process is repeated for the hydrochloric acid. The given amount from the word problem and the conversion factor from the balanced equation. Here again, the matching units are placed diagonally to each other so that they will cancel. According to our calculations, we have enough manganese 4 oxide to produce 60.98 grams of chlorine gas. We also have enough hydrochloric acid to produce 23.44 grams of chlorine gas. Once again, we will only get the smaller amount because once we reach a production of 23.44 grams of chlorine gas, we will have run out of hydrochloric acid. There are several advantages to using the EBM over multi-step dimensional analysis. The equation-based method is faster, less prone to error, and easier to understand. It has the additional advantage that it works every time. I hope that you have found this presentation helpful, and I thank you for your time and attention.